So in this question, we need to find the number of ordered pair A comma B from this set which is given to us, which is having numbers from 1 till 5. So that the function, given function fx is an injective mapping for all x belonging to real number, right? So now what is injective? For those who don't know, injective also means 1 function, right? So before starting the solution, let's take a look at an important property. Okay, so what property we are going to study here? So not directly going to solve the question, but we need to look for the property which is getting applied here for those who don't know about it. So a cubic function is injective on R if and only if its derivative doesn't change sign on R, right? So I'll repeat it again. A cubic function fx is injective or 1 on R if and only if its derivative doesn't change sign on R. So I'll also prove it first before starting the solution. So we can take any arbitrary cubic function, but we are going to take this one which is given in the question for our simplicity of understanding. So we'll first find the derivative of this function. So it comes to be x square plus ax plus b, right? Now why? So one can ask question that why fx greater than 0, greater than equal to 0 for all x belonging to R. Why we are saying that its derivative must be greater than 0 for all possible values of x in R. So we are assuming that fx can be both positive and negative, right? Okay. So what our statement was that its derivative does not change sign. Okay, but now we are saying that it must. So we are saying that why it should not change its sign and why it must be greater than equal to 0 always. Why? So to prove this thing, we are assuming that okay, let's say it can change sign and it can be both positive and negative, right? Now, let's come to the second point. Since fx is continuous, there exist points where it changes sign, right? There might exist some points where the function, whatever we are drawing, where it can change its sign, right? So the graph will increase somewhere and decrease somewhere. Okay. So we are assuming, so why we are saying that? We are saying it based on the assumption that fx can be both positive and negative. So remember, what does f dash x, what do we mean by saying that f dash x can be greater than or less than 0? So when it is greater, the function is increasing, and when the derivative is less than 0, the function is decreasing. So we can say, now we are saying that at any point it can do like that. That means a function can go like this and this, and it can have several peaks like this. Okay. So that's what the third point is saying, that the graph will increase somewhere and will decrease somewhere. It's non-negotiable because we are assuming that f dash x can change its sign. So in other words, the graph will change its concavity, right? This is the point about which the graph is changing its concavity, right? It is concave on upside, it is concave on downside. So that is the point. So that's another way of saying that graph is increasing and decreasing. Okay. A cubic with positive leading coefficients has range to be negative infinity when x tend to negative infinity. That is pretty simple. So let's see this cubic only. So we know that if we make the cube of a very big number, it is obviously going to be big by the another squared number which is at the back of it. No matter whatever coefficient we put here, the cube, it is always going to be greater than its cube, right? Yeah. So that's why it will dominate, and whatever value of x we'll put, the range of that function is also going to be there. So when x is tending to plus infinity, fx will also go to plus infinity. All right. So now, since we said that fx can change its concavity, so we have drawn a function where it is increasing at some till some point, then decreasing till some point, right? Then again increasing till some point, then again decreasing, then again increasing, right? So this is the function which we have drawn. just for our knowledge. So now when we closely look at this function, cubic function, and we try to find the solution of it, so we draw some line, right? For example, this point is a solution of that, and we compare it with another red line which is being showed here. Now we can see that the graph is showing three solutions for this line, right? 1, 2, and 3. And we also note that x1 is less than x2 is less than x3. So x3 is the greatest, right? And we can see that on all three of the values of x, the y part of the function or the value of the function fx is same, right? fx1, fx2, and fx3, it is same, right? Okay, so now we'll try to understand it visually, right? So if we map the function from x to y, so what the condition above is saying that if x has three possible roots, not x, if the function has three possible roots, then and all of the roots are giving one value, that is y1. Okay, so the other values are untouched, right? That means fx is not 1 1 or injective, because for what is the condition for 1 1, that all the mappings must be to unique terms, right? x1 must be to y1, x2 can be mapped to y3, and x3 can be mapped to y2. So this is the 1 1 function. All the parts in the domain can only map to one unique part in the range, right? But this is not the case which is happening here, right? All three terms are being mapped to the same y1, right? Okay. So this contradicts our initial assumption, right? So we assumed initially that the function is injective, right? We assume that. Now we are saying that when if f dash x changes its sign, the function is not able to remain injective. So which is contradicting our initial assumption when we say that it is injective. Okay. So now coming back to our question. Okay, before coming back, I'll again read the statement and now it will make sense to you. A cubic function fx is injective on R if and only if its derivative doesn't change sign on R. Now you get the point. The derivative, it cannot afford to be changing its sign. Okay, all right. Okay, so this was the given function to us. I have written it again, right? This is the given function. Now, using the proven condition for a cubic function to be injective on all real numbers, it must be strictly monotonic. Okay. So f dash x, for being strictly monotonic, f dash x has to be greater than equal to 0 for all values of x belonging to R. That is the condition of being strictly monotonic. So we are substituting again. Now, to ensure that this quadratic equation for all values of x belonging to R, whatever we substitute in this equation, the value of f dash x must be greater than or equal to 0. So how do we ensure that the d of the discriminant of this equation must be less than 0, or it can also be equal to 0? Then we substitute this, right? So discriminant is b square minus 4ac, right? And here b is a is 1, and c is b. Now we get this thing, this relation between b and a, that b square is greater than equal to a by 4. Okay, so now we know that a and b are limited in this set. So we cannot choose a and b on from our own mind. It has to be from 1 to 5, right? So now we are counting the pairs of all possible values of a and b using this very important relation that we generated. So now we can change any one of the variable, either b or a, and check for the other. In this case, we are variating a and checking if b is satisfied, right? So if we take a as 1, a square by 4 becomes 0.25. And how many values of which b can take? So b must be greater than 0.25 in the set. So b can be 1, b can be 2, b can be 3, b can be 4, b can be 5. So b can take 5 values. Similarly, for all these values of a, b can take these values. And finally, the total number of values which B can afford is 15, right? So now what we have to find that for that how many pairs of A and B are possible. So 15 pairs are possible, right?